Welcome to Brain Vision.
Okay, so this question asks us to calculate the temperature between the joints or the points where a brass rod and a copper rod are joined together. All right, and we told that in this question that we have the brass rod fixed inside boiling water, and then we have the copper rod, one of its end, also fixed in ice and water mixture. All right, so let me draw this diagram to represent the situation that was we've been asked to solve. All right, so this is my cup, let's say my bowl containing boiling water. All right, and then inside it is a brass rod. All right, and then let's say this is my copper rod. All right, which is also fixed inside an ice and water mixture. Ice and water mixture. All right, so this is it. Ice and water mixture. All right, forgive my diagram. Okay, all right. So we told that the brass has a length of 0.200 meters, and then the length of the copper is 0.800 meters. All right. Now we want to determine the temperature, the common temperature between the joints where they are joined together. That is the point where we want to determine their temperatures. All right. Now we need to understand that heat always flows from a hotter region to a cold region. All right. And we know that the brass rod, which is fixed in a hotter water, will have heat flowing through it to the cold area inside where we can locate our copper. All right. So in this situation, we're going to talk about heat current. All right. Now the equation talking about heat current is giving us the heat current. H is giving us the thermal conductivity times the area into bracket the change in temperature minus, let's say the hotter one minus the cold one divided by the length of the rod that we are considering. Length of the rod that we are considering. Now, in this question, since we're talking about two rods, we're going to change up this equation a bit to suit the situation that we are studying. All right. Now, since there is a common temperature between the joints where this rod are set up, then we need to change our equation to look like this. K, let me say K subscript B, that stands for brass, times the area into bracket T subscript H minus, now the common temperature we're going to represent with T, all right, divided by the length, the brass, L subscript B. And all of this is equal to K subscript C times A into bracket TH, to bracket T minus TC. Now T minus TC, because the T will have a higher temperature than the temperature at the cold area. And all of this divided by the length of the copper rod. All right. Okay. Now we need to also understand this, that the joints where we have their temperatures the same, what it means is that the heat current at that point in both rods are the same. So we can straight away go away and equate these equations. We need to understand that. All right. So we have our length, the length of the rod already given. Okay, I've already written that. So our thermal conductivity for brass is giving us 109. We can look up that in most textbooks or search them online. Watts per meter per Kelvin. And then that of copper is 385.0 watts per meter per Kelvin. All right. Good. Now let's go on straight away and put in these values. Okay, before that, let's compare the temperatures. So we're going to work in Kelvin, and then later when we're done, we convert it to degrees Celsius. So we know the temperature at the hotter end of the brass is 100, converting to Kelvin plus 273.15, and that will give us 373.15 Kelvin. Now the same applies to T subscript C. It is 0 plus 273.15 is equal to 273.15 Kelvin. All right, so these are the two temperatures that we'll be working with. All right, so going straight away to putting our values inside the equation. We have 109 into bracket 373 minus t, all of this divided by the length of the brush, which is 0.200, will be equal to 385 into bracket t minus 273.15. Forgive me, I beg your pardon. I've let go of the 0.15. Always remember that there should be a 0.15 at the end there. Okay, divided by 0.00. Okay, all right. So when we do that, this gives us 40657 minus 109 t divided by 0.200, which is equal to, into bracket, 385 t minus 15150. 105. I beg your pardon. Divided by 0.800. Okay. So when we do that, this gives us 325.6 minus 87.2t is equal to 77 t minus 21021. So when we group when we group the t on one side and then the other numbers on the other side, they should give us 32525 plus 21021 is equal to 770 minus 87.2t. All right. So this should give us 53546 is equal to 164t. Now when we subtract, or we divide, when we divide, that should give us 326.5 Kelvin. Now remember, we already converted to Kelvin, so we can change it to degrees Celsius, which is also equal to 53 degrees Celsius. Now the question tells us to calculate the mass of water, ice that melts under a time of 5 minutes. All right, so the equation that we can use, now let us not forget, the heat current is also giving us the heat energy divided by the time taken. Okay, now since we are comparing the heat current, we need to understand that during the change of state of ice to water, then we should be talking of what? The latent heat of fusion. Okay, so we can see that the heat given out will be equal to ml subscript f. Okay, ml subscript f. Now we term that 5 minutes under 5 minutes. So we know that 5 minutes is equivalent to 300 seconds. 5 minutes equivalent to 300 seconds. We should understand 1 minute is equivalent to 60 seconds. And therefore, if we have 5 minutes, that should give us about 5 times 60 divided by 1 minute. So this is minute and this is second. So the minute cancels minute, and then we are left with seconds. So we need to understand that. That is how come we have our 300 seconds right here. Okay. So when we go on, let's just put in the values inside this equation, then let's see what we get for that. All right. So let's move on. So we have H equals, using one of the equations concerning the copper, or using the equation concerning the copper, 385 multiplied by 0.005 into bracket 53 minus 0 divided by the length, 0.8, is equal to, this gives us 127.5 joules per second. So we've calculated the heat first. So that's what we've calculated. All right, and then next we go on to calculate the latent heat times the mass. So let's straight away equate this. So 107.5 is equal to the latent heat, which is the mass of the ice, which we have to calculate, times the latent heat of fusion of ice or water is given us 334 0.000. Okay, now divided by the time, which is 300 seconds. That should give us 34000. M is equal to 38250. Remember, this multiplied by this. That is how come we have this. All right. So making mass the subject, we have 38250 divided by all of this. 4000, and that should give us 0.115 kilograms. So that is the mass of ice that melts under the time frame of 5 minutes. Under the time frame of 5 minutes. So our mass is equal to 0.115 kilograms.